Okay, hi everyone. So as promised, this is a screencast that picks up right where we left off in our class, and I'm in this room with Leo. Leo, do you want to say hi?
Hi everyone.
Leo is in this room doing, what are you doing, Leo?
I'm doing the poster for the math club.
He's doing the poster for the math club. Actually, it's the math team, I see.
Well, it used to be the math team, it's the math club now. So
Oh, okay.
this is really old poster.
Got it, got it. So we are doing well, I'm doing a screencast, and Leo's just here doing something on his MacBook. Anyway, let A equal a 2 by 2 matrix, okay? And what I'm going to do here is just give you a general 2 by 2 matrix, okay? A, B, and C, D. I talked about the inverse of matrix A, and I talked about the inverse of matrix A existing such that if the inverse and if A has an inverse, then I said that A times the inverse of A should equal I. Okay, and I is called the identity matrix. And the identity matrix serves the purpose similar to the number 1 in real number multiplication. And let me tell you what the identity matrix looks like for 2 by 2. Okay, 1, 0, 0, 1 is the identity matrix I. We can call it I sub n, or actually I sub 2. It's the identity matrix for a 2 by 2, okay? Which I'm sure will lead to your question, well, what about I sub 3 and I sub 4? And we'll get there, okay? And maybe you're wondering, like, how do I know that this is the identity matrix? And maybe you'll play with a couple of matrices. Maybe you'll look at something like this, like 2, negative 3, 4, negative 7. And if you multiply this by 1, 0, 0, 1, and if you do it fairly swiftly, you will see that the matrix that you get when you multiply is right here. Okay. Similarly, if I take a look at the identity matrix 1, 0, 0, 1, and I multiply it by a 2 by 2, okay, you will also get a 2 by 2, and the result will be just that. And again, if you don't believe that, you can go ahead and try it. Which brings me to one point here. One thing that we've hopefully seen is that unlike multiplication of real numbers, in which A times B equals B times A, in other words, multiplication of real numbers commute, matrix multiplication does not commute necessarily. In other words, in general, if I have matrix A times matrix B, one cannot conclude that this will equal B times A, all right? And if one thing you can think about, like, how about this? Like a 4 by 3 times a 3 by 5, right? Just dimensionally, if I tried to reverse the order, if I tried to commute matrix A and B, here you can see this matrix multiplication isn't even possible. Here it is, all right? That's not to say that in some cases matrix multiplication does commute, but that's the exception rather than the rule, all right? The other thing to note, though, now that I've said that, is if you have the identity matrix I, where you place I, if it's A times I or I times A, when you're multiplying by I, okay, the identity matrix, that multiplication does commute, okay? So a couple of things to point out that I hope I have not glossed over quickly is we're talking about a 2 by 2 square matrix, okay? And I'm talking about the inverse of a 2 by 2. And you're probably wondering, do inverses only exist when the matrix is square? Okay, the answer is yes. So there is no inverse of a non-square matrix. Even if inverses do exist, they will always be of a square matrix, okay? So now let me go ahead and define what the inverse of a 2 by 2 is. If you have a matrix that is a 2 by 2, okay, then the inverse is going to be the following. It's 1 over AD minus BC times, and look what happens here, DA negative B negative C. I know that seems very, very clumsy. And it's absolutely against one of my golden rules of mathematics and in general, I mean, I guess in life too, to just give you something or just to be told something and be told, believe this blindly, don't question it. That goes against everything I believe in. But here, what's funny is that I'm gonna say to you, here, just take this blindly for now, because we will derive this actually in the next lesson. And so I'm trying to follow along. Your text here kind of reverses two ideas. I'm just kind of going with your text. So this will be proven later. Okay, let's make sure we understand what's going on here. Let's just do an example. So let's say I have a matrix A. Go ahead and use the one I used up here. 2, negative 3, 4, 2, negative 3, 4, negative 7. Okay, and let's say the instructions are to find the inverse of matrix A. Okay, the inverse of matrix A is going to be the scalar. This is called a scalar multiple, right? A factor that's multiplied by all the entries of a matrix is called a scalar multiple, this number here. So 1 divided by AD, this is negative 14, minus negative 12, times, okay, we swap these two, negative 7, 2, we negate these, so 3 and negative 4. Now let's simplify. This becomes negative 1/2 times negative 7, negative 4, 3, 2. And what I'm going to do now is multiply this scalar multiple by all the terms inside. And I get the inverse of A is equal to 7/2, negative 3/2, 2, and negative 1. Okay? And now let's just show that this is indeed an inverse. If this matrix was the inverse of A, then it should be that A times the inverse of A should equal the identity. Okay, let's show that. Let's see. 2, negative 3, 4, negative 7, multiplied by the inverse of A. Okay, I'll let you go ahead and do that on your own to show that when you multiply these two, you do get the identity. I'm going to do it right now. Pause. Okay, here's my work below. I just tried to show it clearly this way. I know that the result here is going to be a 2 by 2. Here is the first column, and here's my work for finding the first column. Same thing for the blue column, doink, doink, doink. And I've shown that A times the inverse of A equals the identity matrix. This right here being I. Okay, and I'm not going to show the reverse, the commute of this inverse of A times A. If you'd like to, you can go ahead and do it on your own. All right, so that leads me to ask you this, okay? If we look at the definition of the inverse of A over here, I hope you are looking at this and saying a couple of things. Maybe you're looking at this and saying, this is an interesting denominator, and I know that the denominator cannot be 0. Okay, and then I hope you're asking the related question, which is, are all 2 by 2 matrices invertible? So let's ask that question right now, and let's see what you think. Are all 2 by 2 matrices, it's called invertible, vocabulary word, okay? A matrix is invertible if its inverse exists, okay? This word here means its inverse exists. Now, I want you to think about this in the world of real numbers. In the world of real numbers, does every real number have an inverse? The answer is yes, except for 0, right? Every real number has an inverse, except for 0. So my question to you is, do you think that every 2 by 2 matrix is invertible? What condition here would make an inverse not exist? Go ahead and think about that with either yourself or someone next to you. And if you're thinking about it with yourself, I hope that you're somewhere public So when you talk to yourself, people look at you as if they're incredibly impressed, okay? But go ahead and think about it. Under what conditions would the inverse of A not exist? And then replay me. Okay, the answer to this question is no. Are all 2x2 matrices invertible? No. And I want you to tell me, when is a 2x2 not invertible? Well, you probably saw that A, the matrix A, is not invertible if AD minus BC equals 0. If AD minus BC equals 0, the matrix is not invertible. Now I'd like you to go ahead and generate 2 examples of matrices whose inverse would not exist. So these 2 matrices are not invertible. Go ahead. Think of 2 matrices that are not invertible and then replay me to compare answers. Okay, so here are a couple I thought about. Okay, so, any matrix where the entries are all the same, okay? Here, if I take AD minus BC, I'd be dividing by 0 in this scalar multiple up above here. Oops, where is it? Right here, okay? So this matrix is not invertible, okay? This one is not. And if you look at this, maybe a little seed is planted here. Maybe you see that, wait a minute, this first row is just 2 times the second row. So these are actually the same row, right? And maybe you'll start something will sort of tickle in your brain. You'll say, wait a minute, I remember we had augmented matrices. If we had, the same row, something happened. But again, all those little loose threads are hopefully dangling in your brain, and we're going to tie them all up really nicely. Here, this is a pretty cool example, okay? A column of zeros. If there's a column of zeros, or for that matter, if there were a row of zeros, do you see how your matrix would not be invertible, right? Okay. So let me give you some vocabulary. A non-singular matrix, okay, saying A is invertible means the inverse of A exists, okay? Saying A is invertible is the same thing as saying A is non-singular. So again, I'm going to use my party analogy, which I know I always come back to, and you probably are getting tired of it already, but oh well. Okay, describing a matrix as non-singular or invertible, these are synonymous, okay? Similarly then, if I say that A is singular, okay, let's think about this. If A is singular, this means that the inverse of A does not exist. Okay, I guess we can also add this. And if the inverse of A does not exist, then we can say that A is not invertible. All right, so these vocabulary words, they're synonymous, or these vocabulary phrases are synonymous. Not invertible, singular. Okay, invertible, singular. You can pick your poison. All right, now let's bring this is a little bit long, I realize, but maybe I'm just a little bit excited because this is our first screencast anyway. So let's say we've got this going on, okay? Let's say we have this system, okay? Now watch this. We have this system, 3x minus 2y equals -1, 4x plus 5y equals 3. And remember, in our last class, I talked about generating a matrix equation that looked like this. Okay. You'll often see this matrix equation described in general as this. You'll see it described in general as AX equals B. Okay? This is kind of like the slope int form of a matrix equation. Why this is called a vector and this is called a vector, I'll tell you only briefly now. But when you have a matrix that is just a column, or just a row, it's often referred to as a vector matrix because this describes components of a vector. If you're not in AP Physics, this may not make sense. And like I said, linear algebra usually comes after multivariable. So we'll talk about this vector stuff a whole lot more in linear algebra. The point being, you'll see AX equals B is often referred to as generating a matrix equation where you have, A is the coefficient matrix, X is the variable matrix, and B is the constant matrix. Okay? All right, what I want you to do right now is, would you please go ahead and find the inverse of A? Okay? And then replay me. Okay, here is the inverse of A. Okay, you agree? All right, now I'm going to go back up to my equation, and what I'm going to do is multiply both sides of these equations by the inverse of A. But here's what's very important, right? In matrix multiplication, the order matters. The order matters and the grouping matters. So when I look at this left-hand side, okay, there's a 2 by 2 already multiplied by a 2 by 1. The only way to multiply A by inverse of A on the left-hand side of the equation is to multiply, watch me over here, okay? I'm going to multiply both sides of this equation over here. Multiply it by the inverse of A. But this is an equation after all. If I multiply on the left by the inverse of A, I have to multiply on the left, on the right-hand side by the inverse of A, because again, the order in which you multiply matters here when we're solving an equation. This is different than solving an equation with real numbers. So I know, I'm not going to do it out because I know this is going to happen. When I multiply these two, I'm going to get the number 1 in air quotes, right? Or in matrix world. This is going to give me this times xy equals, now I'm going to multiply the inverse of A, 5/23, excuse me, 2/23, negative 4/23, and 3/23. Multiply this by here is matrix B, 1 and 3, okay? What I'd like you to do is to please go ahead and do this multiplication out and pause me, okay? Now, when you do this, oops, did I lose negative 1? Oh, whoa, holy mommy. Okay, that's a negative 1 there. Whoops, negative 1 here. Okay, do this multiplication out and then come back and find me. All right, after I do the multiplication, I know that this left-hand side is equivalent to just saying xy equals, when I multiply this out, confirm it, when you confirm with your work, I get here 1/23 and 13/23. Okay, and what have I found, boys and girls? This is the solution to my system. The solution to my system. Okay, x equals 1/23, y equals 13/23. Okay, so I'm going to leave you with a couple of questions for homework, and I'm going to ask you a question to think about as well. What do you think? What do you think I sub 3 equals? In other words, what do you think is the identity matrix in the world of 3 by 3s? Okay, you can just play around with this and just see what, I'm curious to see what you come up with. In the world of 3 by 3s, I can tell you this, the identity matrix is going to be a 3 by 3. Okay, so what do you think the version of 1 in air quotes is in 3 by 3 world? All right. Okay, I also noticed a vocabulary word, which is this, a vocabulary phrase that you may come across. 2 matrices are what is called row equivalent. Row equivalent, okay? Actually, now that I think about it, I think we did this vocabulary word in the very first day. 2 matrices are row equivalent if an elementary row operation manipulation of one matrix yields another. Okay, if an elementary row operation performed on one matrix yields the second matrix. So do you remember when we were solving all of those augmented matrices on the first and second classes? And remember when we take an augmented matrix and try and write the augmented matrix in reduced row echelon or row echelon form? Each step along the way, remember how we would say, okay, 2 times R1 plus R3 gives me a new row 3, right? Okay, so when we change matrices, when we kind of our matrix evolved in that process, each new matrix we got in that step was row equivalent to the one before. That's what this word means. All right? Okay, let me give you your homework. Actually, I'll post homework on the calendar. Okay, bye. I hope this helped. I hope you enjoyed it.